In this lesson, we're going to take a look at something called Benford's law. According to Benford's law, data sets, many data sets, have the property that the leading digit, or the first digit, follow a distribution that's shown here in this histogram. Primarily that a leading digit of 1 occurs the most, about 30% of the time, whereas larger digits, 8 and 9, as the first digit, occurs less than 5% of the time. This distribution is quite interesting because electricity bills, street addresses, stock prices, population numbers, death rates, lengths of rivers, physical and mathematical constants, and processes described by power laws, common in nature, tend to all follow Benford's law. Now, here's an example. In this table, this first row of leading digits represents our categories. So 1, 2, 3, up through 9 as our leading digit. This second row here, this is Benford's law, the percentages for each one of these leading digits. So 1 represents 30.1% of the time, 2 shows up about 17.6% of the time, all the way down to 9 at 4.6%. And then down here on the third column is our example. So we have a sample of leading digits, and this is internet traffic arrival times. So we're looking at some kind of time in regards to the internet. The leading digit of 1 in this data was observed 69 times. The leading digit of 2 was observed 40 times, etc. The question is, do these frequencies fit Benford's distribution? We are given that these leading digits equal 271 if we were to add them up. So we're going to try to see if Benford's law would apply. This is still a goodness of fit test. We're wanting to know, does the observed data in my table fit a particular pattern, a particular distribution? So here we go. First up, we've got to check our requirements. We've got a randomly selected sample from a larger population. The sample indicate frequency counts, and each expected frequency is at least 5. Now, how do I know that part? Well, I'm going to scroll down to the table here a little bit. Looking at these frequencies in Benford's law, the smallest frequency is 9. So if I take 4.6% and I multiply 0.046 times 271, which is how many observed frequencies I have, those numbers total to 271. Multiply those together, and we get 12.466. That's greater than 5. And that's all I really need to check, because all of these other percentages are bigger than 4.6%, so they will all be bigger than 12. And that's why I only need to check the smallest one. So we have all the requirements satisfied. The claim is that the leading digits fit the distribution as Benford's law. So we can write each one of these probabilities corresponding to the percentages. We're really trying to get down into what are our hypotheses. If the original claim is false, at least one of the categories does not follow Benford's law. We have our null hypothesis, which we can state as numerical, or we can say the data follows Benford's law. And then our alternative, at least one of the proportions is not equal to the given claimed value. Or we could say at least one category does not follow Benford's law. And we say at least one category because we only need one to mess it all up so that it does not follow Benford's law. We only need one example to throw it out of kilter. Significance level is not specified, so we'll just choose alpha as 0.05, and we'll use the goodness of fit test for this. First up, though, we've got to calculate the expected frequencies using Benford's law calculations, so we're going to use Excel or Google to do this. So I'm going to set up my table a little bit differently than what's given on the handout. I'll put my observed frequencies in first. And then for my expected, I'm going to first put in Benford's law, but as decimal numbers instead. And I do this for the sole reason of being able to calculate my expecteds. Now, if the problem didn't give me my total, I could very easily calculate my total here just by typing in sum. And I get that 271, adding up all of my observed frequencies. For the expected, now I can say 271 times the Benford's law calculation. And what makes Google and Excel so great is I don't have to keep typing in equals 271 and click on that Benford's law. I can just drag those across and I get my expected frequencies according to Benford's law. And notice how they go down. The largest is in 1, all the way down to the smallest at 9. And we see that 12.466 that we've seen before in checking those requirements. Now let's perform our chi-square test. So chi-square.test, we need to put in our observed frequencies first. So we'll select those. And then we put in our expected frequencies. I would just use what's in your spreadsheet. Don't worry about rounding or anything like that. Just use the straight calculations. Close our parentheses, hit equal. We get 0.186376. So 0.186 is what that chi-square test gives us back. Well, what's great about this p-value of 0.186, we compare that to alpha equals 0.05. So if we compare 0.186 to alpha, our p-value is greater. If we were to draw our chi-squared distribution, alpha being 0.05, keep in mind that corresponds to our critical value. And even though we're not getting our critical value, I'm using this graph just to show you the connection between the p-value and the traditional method of hypothesis testing. P-value is 0.186 since that's much bigger. That p-value means we're to the left of our critical value. And since our test statistic is to the left, we do not reject the null. So there's not sufficient evidence to reject the claim that these leading digits correspond to Benford's law. It seems like they do. So summing up, just as we said, step 7, p-value 0.186 is greater than our significance level, so there's not sufficient evidence to reject the null. And this sample does not provide enough evidence to conclude that Benford's law is not being followed. And if we look here, we can see a graph of the proportion. In green is Benford's law, in red is our observed values that we were given in the table. And we can see that the red graph seems to follow that green line pretty well. It's not perfect, but it's close. Now, why in the world would we care about this? If we have a situation like this where we have internet traffic arrival times, if the data did not follow Benford's law, there's a possibility that a hacker could be trying to get into some data. And so having this information might help us track down some nefarious activity. It used to be when checks were written very widespread. Forgeries were often found because the checks did not follow Benford's law. So it seems natural to assume that the leading digits would come in a uniform pattern, but that's where Benford's law is so surprising and interesting, that it does not happen in that case. So in 1938, a physicist from General Electric named Frank Benford found this distribution by observing a lot of data. Benford's law lends itself nicely to helping detect fraud because of that very assumption of uniformity. When people are making up numbers, they tend to keep those numbers uniform. It makes for an interesting situation. back when checks were written a lot, they could find suspicion of fraud just by looking at those leading digits and whether it followed Benford's law. And we don't write checks so much anymore, so other examples of data would pop up, like these internet arrival times. There could be a hacker involved or some kind of internet intrusion that would cause the data not to follow Benford's law rather than being just natural.